Welcome to my channel, STEM Cafe. Where we make everything science, technology, engineering, and mathematics easy to comprehend, assimilate, fun, and entertain. Today we are dealing with specific aspects of series, convergence and divergence. What do we mean by convergence and divergent series? A series in which the sum Sn of n terms of the series tends to a definite value as n tends to infinity is called a convergent series. If Sn does not tend to a definite value as n tends to infinity, the series is said to be divergent. What do we mean? We have series, and sometimes the series, there is a formula for the sum of the series, So, if after summing it, and you can look at the value of the series that at n term, if you sum it to n terms, it's going to give you certain value. Instead of n term, you look at it that if it is something like infinite value, infinite, the series is towards infinity, you can get a definite value for it. That's when we talk about it as convergence. You can have a definite value for it. But when you cannot ascribe a value to it, you refer to that as divergence. And in mathematics, there are so many kinds of series. If the series is convergent, it is useful for us. Most of the time, we look at ways of getting the value for infinite series. And if you can get that value, we refer to that as convergent series. But if you cannot get it, some instances, we refer to that as divergent series. Let's look at geometric series. Look at this one now. We have something like 32 plus 16 plus 8 plus 4 plus 2 plus 1 plus half plus, and then to infinity. You add everything to infinity. We have a formula for this. Since this is GP and geometric series, we have a formula for it, as in Sn equals to A into R raised to power n minus 1 by R minus 1. And what is our A? 32. Our R is half. So minus 1 divided by half minus 1. So we can still swap this one at the end of the day. From our knowledge, if this one is made to be infinity, half raised to power infinity will tend to 0. You understand? So at the end of the day, this will give us 32 into minus 1 divided by minus half. So we are going to get 64 for this. So you can see, this series now, at infinity, we can ascribe the value to it. This one is convergent as it is. This one is convergent. So, we notice when we have something like geometric series, when R, common ratio, is less than 1, we can easily talk about convergent series. There are several kinds of series. This is just an example of infinite series. There are several series, but I'm just giving an example to show that when the series tends to infinity, we can get a value for the sum. And at that stage, we can refer to that series as convergence. So with this concept in mind, we can talk about infinite series. So I've just given you an example of infinite series. Infinite series can be in several forms. You can have it like this. 1 plus 2 plus 4 plus 8 plus 16 plus. Once it goes to infinity like that, we can refer to that as infinite series. So the reason I'm talking about this is as n tends to infinity. You can see. So note this. This is the first condition when you want to talk about convergent series. The series, you must look at the sum towards as n tends to infinity. That is the first one. The second one is talking about the value at infinity. The value of the sum at infinity. And that is why we talk about limiting value. So, with the knowledge of limiting value, you will be able to solve, to get a value, to be able to, work out the value or the sum of the series if it is convergent at infinity. Look at this. For this one now, by the time I look at this one, I will not be able to find any value for it because it will be divergent. So, for limiting value, the major thing we look at is if we have found the value of the sum towards infinity, and then we have a formula for Sn, e.g. for geometric series. We say this one is equal to A into 1 minus R raised by n over 1 minus R, depending on how you want to arrange it. If I can substitute infinity for n here, and I can find the value. So under this situation, the limiting value, I can get the value for this, and then I'll be able to say it is convergent. If I'm not able to find that, it is divergent. And this also helps me in some tests to know if it is convergent and or divergent. We get there. So the knowledge of limiting value is very compulsory, especially when n tends to infinity. So these are the conditions you need to know concerning limiting value when we are treating convergent and divergent series. 1. When r is less than 1 and r tends to infinity, and r is raised to the power of infinity, you can see r is raised to the power of infinity, just like you say x raised to the power n. So this one will give us 0. R is less than 1, so this one will give us 0. Another thing I want you to know is this: 1 over n. You can see when we have a situation like this 1 over n, and you want to talk, and we say that n tends to infinity, so we can say it is something like this 1 over infinity. That one gives us 0. So you can see that one gives us 0. Now another one is 1 over r raised to power infinity. You can see when r is greater than 1, r is greater than 1, you can see it means that this one can be set to tend to 0. So with all this little knowledge, you'll be able to find the limiting value and then ascertain if the series is convergent or divergent. In mathematics, most times convergent series are the ones that we are concerned about, and that is why we need to do work on this, and so then we do some tests on the series to know if it is convergent or divergent. There are some conditions to make you know fast that a series is convergent or divergent. Before we go on, let's look at how divergent series looks like before we go deep into convergence. Now let's look at how divergence can be. If infinite series ak from k equals to 0 to infinity converges, we mean that the sum Sn of n k equals 0 to n have a limit as n tends to infinity. That is, there is a limit. You understand? We now say if it does not, we say the series diverges. The same thing as what you have said before. Now let's go towards the main thing. Divergence can be in any of the following ways. 1. Divergence to positive infinity. Look at it. 1 plus 2 plus 4 plus 8 plus 16. Like I said before, in this instance, r is greater than 1. Divergence to negative infinity. Look at this one. Minus 1, minus 2, minus 4, minus 8, minus 16. You can see. In this instance too, r is greater than 1. Now look at the third one. Oscillating finitely. That is, at a point, this one can have a specific value. At the other point, it can have another specific value. But it will always change from that, between the two values. Like this one, if you look at it, the answer will either be 1 or 0. 1 or 0. 1 or 0. That is how it will be like. Oscillate infinitely. This one too is changing. It depends on what term is that infinity. And there is no specific value for it. This one is, is fluctuating. It can go up, it can go down. It can go up, it can go down. That's why we say oscillates infinitely. Now let's look at another aspect of convergent series. Now we have talked about limiting value before. Limiting value knowledge is very necessary in finding the value of the convergent series at infinity. At the same time, it's also useful in doing some tests to know if the series is convergent or divergent. Most of the time, under this convergent and divergent series, we talk about when n is at infinity or tends to infinity. So I just use this example to show the relevance of limiting value to this topic we are treating. Now, I said it, that we talk here mainly when it is at infinity. It can be at even 1 or 0, depending on what topic we are dealing with. But when we are talking about convergent and divergent series, you always look at it at when it is at infinity. Sometimes you might have what's it called? Fraction. And sometimes you might have it as a multiplication. But most times it is as fraction. What we deal with under convergence and divergent series. Now look at this question now. Find the limiting value of n cubed plus 3 over 2n cubed plus 3n minus 4 as n tends to infinity. Here, when n tends to infinity. Now let's look at it. You have n cubed plus 3 divided by 2n cubed plus 3n minus 4. Because we are talking about infinity. And the only time you can have reasonable value when we have n at infinity is when we have it as 1 over infinity. So, I told you before that 1 over infinity is 0. So, what do we do next? We divide both the numerator and denominator by the highest possible value of n. So here, n cubed is the highest possible value. So divide numerator and denominator by n cubed. So you can see, you have it like this. So you have n cubed plus 3 over n cubed, 2n cubed over n cubed plus 3n over n cubed minus 4 over n cubed. You know, when n tends to, okay, before we get there, so this will be 1 plus 3 over n cubed divided by 2 plus 3 over n squared minus 4 over n cubed. Now, when n tends to infinity, this one will give us 3 over 2 plus 3 minus 4 over. You can see this one will be very large, this one will be very large, this one is already large, very large. So at the end of the day, I'm going to have 1 plus 0 over 2 plus 0 minus 0. So that will be 1 over 2. So when we are talking about infinite or infinity, this is how we always do it most times. We reduce it to fraction and then possible fraction. So at the end of the day, when we slot in the value infinity, we are going to be having 0, 0, 0. So you can see. So with this, let's look at the conditions that once you look at a series, you'll be able to say, oh, this series is convergent or this series is divergent. So that's what we are looking at next. Test for convergence. Now, when you have a series and you can observe it, and then you can conclude that at the end of the day, when the series tends to infinity, the term will tend to 0. The term will tend to 0. So the first test is a series cannot be convergent unless its term ultimately tends to 0. That is at infinity. The last term you can say is 0. But if the term does not tend to 0, the series is divergent. And I told you the other time, when you look at something like this, when you look at this, anything like this, 1 over alpha, infinity, 1 over r raised to power n, if r is greater than 1, r raised to power n, when r is less than 1. So all these ones will give us 0. But when it's otherwise, we are going to have infinity. So if we can be able to break the last term down at infinity, like this one now, will give us 1 over r raised to power infinity. So that one will give us 0. If r is greater than 1. For this one, if r is less than 1. So you can see, because as it is going forward, the term will be reducing. But if you cannot confidently say this, you will use another test. There's another test available. So that's why I'm reiterating all these points. That's why I'm emphasizing and repeating it. So the first thing you look at is, if I should look at this term, will the term give me 0 at infinity? If you can confidently say yes, that series is convergent. Now let's look at another possible test. Now the second test to know if you can use to know if a series converges is called comparison test. In this place, we have to know another series which is confirmed to be convergent. A series of positive terms is convergent if its terms are less than the corresponding terms of a positive series which is known to be convergent. As I just said, you know another series which is convergent, and then you compare the terms of this series with that convergent series. If the series you are using to compare the non-convergent series is lesser than the terms of the convergent series, the series is said to be convergent. Similarly, if the series is divergent, if its terms are greater than the corresponding terms of a series which is known to be divergent. Very simple. We are now told that useful series for comparison is 1 over 1 raised to power p plus 1 over 2 raised to power p plus 1 over 3 raised to power p to 1 over n raised to power p plus to infinity. So we are given the terms for the summation. That is 1 over n raised to power p from 1 n equals to 1 to infinity. Now we are now told if p is greater than 1 in this series, it is convergent. If p is equal to 1 or less than than 1, it is divergent series. It is divergent series. Now look at this situation. We have to find if this series 1 over n squared from n equals to 1 to infinity is convergent. You can see from here we are told that once p is greater than 1, it converges. So look at this. We are going to have 1 over 1 raised to power 2 plus 1 over 2 raised to power 2 plus 1 over 3 raised to power 2. So compare with this. You can see these two, the power is the p. And we are told that once p is greater than 1, the series converges. So which means that this one is convergent. It means that this one is convergent. That is it. So when you are given a kind of series to confirm if it is convergent, you can pick any series like this and compare each term by term to know if it will be convergent or divergent. Let's look at another one. Now let's look at another one. You have 1 over n into n plus 1. So which means that you are going to have 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4. So by the time you do this, how do we confirm if it is convergent or divergent? We look at one of this kind of series, establish it or write it out, and compare it term by term. Now let's look at the situation where p is 2. We are going to have 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus. Now let us take it one by one. This one is half, this is 1. This one is less than this one. Half is less than 1. That is to start with. Let's look at the second one. 1 over 6, 1 over 4. 1 over 6 is less than 1 over 4. For the third one, 1 over 12. That will be lesser than 1 over 9. So what does that imply? Since these terms are lesser than this one, which we know to converge, it means that this term is convergent. So just pick one. Establish a term like a series like this. Use it to compare the terms of the given series that you want to confirm if it is convergent or divergent. And by the time you do that, you'll be able to know. You just compare it one after the other. But the only thing is just try to select, the right. Sometimes you might need to go to higher powers, and then from there you know if it is convergent or divergent. Now let's go to the third one. Now the third test is Jalenberg's ratio test for positive terms. And how do we do it? Let's say we have u1, u2, u3 are the terms of the series, and none of them are added together. And let's say u1 plus u2 plus u3 into un to infinity be a series of positive terms. We should now find expression to define un and un plus 1. That is the nth term and the n plus 1 term. And then after that, we will now form the ratio of the nth term, n plus 1 term over nth term. That is un plus 1 over un. With this, we will now determine limiting value, like we have studied initially, of the ratio as n tends to infinity. Now, once we can do that, if our answer is less than 1, the series converges. If it is greater than 1, it diverges. If it is equal to 1, we cannot say it is divergent or convergent. If it is equal to 1, we have to carry out further tests. Maybe using test 1 or test 2. Or we just have to know what we do. Because once it is 1, we will not be able to conclude if it is convergent or divergent. Let's look at an example. Now, let's look at this. Let's quickly apply this. It says, apply the Jalenberg's ratio test to the series. 1 over 2 plus 2 over 3 plus 3 over 4 plus, like that. How do we know if it is convergent or divergent? The first thing is to know, to define what each term will be. For this one, un will be equal to n over n plus 1. You can see. So un plus 1 will be equal to n plus 1 over n plus 2. You can see. So the next thing is to do this. Un plus 1 over un. So un plus 1 over un will be equal to n plus 1 over n plus 2 multiplied by n plus 1 over n. So we are going to have it as n squared plus 2n plus 1 over n squared plus 2n. And in this instance, we know that when n tends to infinity, that's when we are using the test. So, as we did before, we divide denominator and numerator by n squared. So we are going to have 1 plus 2 over n plus 1 over n squared divided by 1 plus 2 over n. So, and as n tends to infinity, this one and this one will be 0. So we are going to have equal to 1. And as we said, when we have 1, it is inconclusive. So we cannot be able to say if it is convergent or divergent. So inconclusive. So for us to know if it is convergent or divergent, we will need to look at the other tests mentioned earlier. So let's see. 1 over 2, 2 over 3, 3 over 4. If, from what we said before, if it tends to 0, it means that it will possibly convergent series. That is, if the term ultimately tends to 0. Now let's look at it. So look at it. Nth term is n over n plus 1. So when n tends to infinity, un will give us n over n over n over n plus 1 over n. You understand? So this one is going to give us 1 over 1 plus 1 over infinity. So we are going to have 1. So since this is 1, this is 1, it means that at infinity, it's not even tending to 0. So this one is giving us divergence. So you can see, if you apply one test and you do not have the, you are not satisfied with the results, you can apply another test. So that's what this example has shown us. Now some theories contain alternate positive and negative terms. Look at this. We have 1 minus half plus 1 over 3 minus 1 over 4. So, since this one has both positive and negative terms, we call it mixed series. And on checking this further, we can see that it is convergent. Now, let's talk about assuming we have a series with absolute terms of this. That is, you can see, it's going to be 1 plus half plus 1 over 3 plus 1 over 4. And on checking this one, we realize that it is divergent. So what we are saying in essence is that if you have a series like this with mixed terms, and you try to add the absolute terms, this can be convergent and this can be divergent at the same time. If this one is convergent, but one thing is sure, if this one is divergent, automatically this one is divergent. Let me give you the condition. It's divergent. If it's convergent, can either be convergent or divergent. But if we have a situation like this, and this one is convergent, then it's convergent. Please try to notice the arrangement. If this one is divergent, this one will be divergent. If this one is convergent, you understand? The sum of the absolute values can either be convergent or divergent. But if the sum of the absolutes is convergent, it means the original is convergent. That's what we are saying. Now, looking at the situation, we are now trying to differentiate between when it is absolute convergent and conditional convergent. So, if we have convergence, we said that it's convergent. Hence, we have it as absolute convergence. It is absolute. But we said that if this one is convergent, this one can either be divergent or convergent. So the condition is that if we have this one as convergent, it's divergent. This one will be referred to as conditional convergence. Conditional convergence. Now let's walk through this. The question says find the range of value of x for which the following is absolutely convergent. If we want to use D'Alembert's principle, here we said un plus 1 over un was less than 1. That's what we can easily use in this stage. Now let's find the expression to define n term. So we have un is equal to x over n plus 1 into 5 raised to the power n. So let's say and this will be like this. So un plus 1 modulus. Because we are talking about absolute convergent place. So it means that this one will be x equal n plus 1 whereby n plus 2 into 5 raised to the power n. And since we are using D'Alembert's principle. We are going to write it like this. We are going to write it like this. X raised to the power n plus 1 over n plus 2 into 5 raised to the power n plus 1 times n plus 1 into 5 raised to the power n over x raised to the power n. By the time you divide this and this one, you are going to have x. This one, you are going to have 5. Now, so we are going to have n plus 1 over n plus 2. And for divergence, for convergence, this value should be less than 1. Now, when we want to have convergence, it means that x into n plus 1 over 5 into n plus 2. And for convergence at infinity, which means that n tends to infinity, must be less than 1. So what does that give us? Let's now do our normal now, so we are going to do it like this. X into 1 plus 1 over n over 5 into 1 plus 2 over n. That is, we divided the numerator and denominator by n. So must be less than 1. You can see. From here, we know that when n tends to infinity, 1 over n and 2 over n becomes 0. Therefore, we have x over 5 is less than 1. It's less than 1. Therefore, for this to converge, x must be less than 5. For this series, x over 2 to 5, x squared minus x squared over 3 to 5 squared, etc. For the series to converge, absolutely, means that x must be less than 5. So with this, we have come to the end of this part. We are still going to further on the series. We talk about power series, Maclaurin's Taylor series, and other stuff. So since we have this foundation, it will be very easy for us to treat those ones. I might treat some questions on this also. So please tune in, and when our next video comes up, ensure you watch it. We make everything simple and clear in this channel. Kindly subscribe if you haven't, share, comment, and like. Thanks. Whatever you feel like you can do, your advice is also appreciated. And whatever you are doing for us to make sure this goes viral is also appreciated. Thank you very much. See you in the next video.